To know before starting this problem is that the Kb of NH3 is 1.76 times 10 to the negative 5, and the Henderson-Hasselbalch equation is pH is equal to pKa plus log base over acid. And just some basic things such as molarity is equal to moles over liters. Problem A of our question asks for the original solution, pH. And so we'll be using the Henderson-Hasselbalch equation, pH is equal to pKa plus log base over acid. And in order to derive pKa, it will be shown in the following. First, we need to take the number of moles in the base, and that will be derived by 0.1 molarity times 0.1 liters, which is we're given in the original equation, and your final answer will be 0.01 moles of NH3 will be used. For that, you'll find the number of moles of acid to be used, NH4+, and this is found by multiplying 0.1 molarity NH4+ times 0.1 liters, which is the amount that were used. And this gives us 0.01 moles of NH4+. That were previously derived will be put into the Henderson-Hasselbalch equation, so log 0.01 over 0.01, given for base and acid. And we will be plugging in pKa, and this is shown by taking the number of Kb and putting it into the equation. pKb is equal to negative log Kb, and this gives us 4.75, which will then be plugged into 14 is equal to pKa plus pKb, and it will be plugged into pKa is equal to 14 minus 4.75, which gives us a value of pKa is equal to 9.25. And this will be very important as it is later plugged back into the Henderson-Hasselbalch equation, which will be pH is equal to 9.25 plus log 0.01 over 0.01. And log 0.01 over 0.01 will equal 0, leaving us with pH is equal to 9.25, and this solves part A of the solution. For part B of our problem, we are given 0.004 moles of KOH is added to our solution, and we will put it into the equation. NH3 plus H2O gives us NH4 plus OH minus, which is our base. And the base is KOH, and it's added into OH minus 0.004 because it is a strong base. And we add 0.004, and we have to subtract from the right side, and we subtract from the right side of 0.01 as well, and we add 0.004 on the left side, which gives us 0.014 NH3 and 0.006 NH4+. Then it is plugged back into the equation. pH is equal to 9.25 plus log 0.014 over 0.006, which gives us pH is equal to 9.62, which is our final solution for part B. In part C, instead of being given base, we are given acid, a strong acid, HBr, and 0.003 moles of HBr is added to the original solution, which is then plugged into this equation. NH4+ gives us NH3 plus H+, and 0.003 moles are added to the H+, which is a strong acid, and it is subtracted from NH3. 0.01 minus 0.003 gives us the amount of NH3 that is after adding 0.003 moles of HBr, 0.01 plus 0.003 on the left side, which then gives us 0.013 and 0.007, which is then put back into the Henderson-Hasselbalch equation again. 9.25 plus log of base, which is 0.007 NH3, over 0.013, which is NH4+, and it gives us the final answer, 10.39 is equal to pH, after adding 0.003 moles of HBr. The final part of our equation is if 0.0150 moles of HCl is added to our solution, and this is what happens. 0.0150 is added to H+, and it's subtracted from the right side, and is added to the left side, which gives us the following values. And once these values are accrued, it's just like problem C, and we put it back into the Henderson-Hasselbalch equation, 9.25 plus log 0.005 over 0.025, which then is used to get our pH is equal to 8.551 pH. Thank you very much for viewing this, and I hope it helped. Thank you.